Hello everybody, welcome back to another video, and today we're going to be talking about when to use each convergence and divergence test. And there are, of course, around 10 of these that you have to memorize, so it's very important to know when you need to use each of them. So for this example here, we have the infinite sum of n over n plus 1. So I'd say the most important tip I can give you in this video is to always first try the divergence test. And this divergence test is basically just testing if the limit as n approaches infinity of the sequence is equal to 0 or not. So for this particular problem, we're just going to take this n over n plus 1, which is our area of interest. We're going to take the limit as n approaches infinity of n over n plus 1. And for it to converge, the limit has to be equal to 0. So for this particular limit, we don't really care about this 1 because it doesn't grow as fast as both of those. So we basically have an n over n type of sequence. So we know that this converges to 1. So that means that the original sum of n over n plus 1 diverges. So the limit as n approaches infinity has to be equal to 0. Next one is the geometrical series test for problems that look similar to this, 3 over 5 raised to the n. It's where you just have one number raised to the nth power, or the n minus 1, n plus 1, anything of that sort. So for this test, all you need to be able to do is to identify the r value in the sample series. So the sample geometric series is a times r to the n, and r is that ratio, that common ratio that we're multiplying each time. So if the absolute value of r is less than 1, then that means that the series converges, and if not, then it diverges. So for this particular example, our r value, which is always the one inside right here, is 3/5. So the absolute value of 3/5, is that less than 1? Yes, it is. So that means that the series does in fact converge. So series converges. So we now have that information. For the next test, the p-series test, all you're going to need to do is be able to recognize this little format, a 1 over a power. So 1 over n squared here. So this series converges if p is greater than 1. So if we had something like 1 over n as a sum, it would be divergent, right? But if we had something like 1 over n to the third, then it would be convergent. So for this particular example, this number right here, p, that we're talking about, is just the power that's on the bottom. So since 2 is greater than 1, then we know that the series converges. Okay, so very, very simple type of thing. Now here is probably the most confusing one, but to be honest, you can get used to it if you already know your geometric and p-series. So next is the direct comparison test. So if the series looks similar to a known p-series or like a geometric series. So the idea is that you have a series like this. You have a series 1 over n squared plus 5. So if you get rid of some of the like the noisier components like this 5 right here, right? If you just look at the 5, it's very similar to the series we had up there of 1 over n squared. So if you compare it with a series you know diverges or know converges, then um, then you can tell that if this one particularly converges. So for this example right here, we know that the sum of 1 over n squared is convergent. So we know that if we just add a plus 5 in the denominator, that's not going to change anything. So we also know that this sum is also convergent as well. Next is our limit comparison test. So if we have two series that have like similar dominant terms, but we can have some potentially like messy inequalities and things like that. So basically, we're checking if both series behave the same. So for example, if we have a series like 3n plus 1 over n squared plus 5, if you get rid of some of the insignificant terms that aren't going to grow as fast, you're going to have a series that's going to look like 3 over n, right? Because n divided by n squared is n. So you're going to have basically a known series of 1 over n, right? So we're going to assign this is the original series is going to be all of this stuff right here, and then b of n is going to be equal to the series we can compare it to. So because 3n and over n squared is 3 over n, we can compare that 3 over n to 1 over n. And that's just the simplest thing we can do because the 3 is not very significant in this matter. So for this calculation, you just do the limit as n approaches infinity of a of n, which is the original, so 3n plus 1 divided by n squared plus 5, and then you divide it by 1 over n. And if you compute this limit, you get 3. So this means that since the harmonic series diverges, that means this series in particular diverges. All right. Next is the integral test. So the way to recognize this is if you have a continuous function that is positive and decreasing. So for example, if you have an infinite sum, usually it's using potentially integrable like quantities, like usually they use like fractions and natural logs and exponents and things like that. Stuff you can integrate. Usually they do not come with factorials or any other type of special thing that's difficult to integrate. So here we have the sum of 1 over n ln n. So for this particular example, what you're going to do is you're going to recognize that we have a continuous decreasing function because we have 1 over a number, right? But we can't use our comparison test because ln of n is significant, right? We can't just get rid of it because ln of n is actually an increasing function, so it's not insignificant. So we need to take it into account. So that's why we're going to do the integral test. So you take the integral from 1 to infinity of 1 over n ln n d, or sorry, these should be x's. X ln x dx. And since this integral diverges, which If you can't tell that it does, then you can do some review on your improper integrals. Then we know that since this diverges, that means that the entire series diverges too. So it's usually if you have a natural log or something, you're always going to want to stick to that integral test or a little fraction bar with some significant things in there. Okay. Next is the ratio test, which is the one where you kind of have to have the most things to remember. So if you have, for example, a sum such as n factorial over 3 to the n, this one is very useful when you have exponents and factorials, um, and also powers like n to the n or things like that. So there is one issue with this test, and it is that if the limit as n approaches infinity equals 1, then we have an inconclusivity right there. But most of the time you won't come across that. Most of the time it'll work out pretty fine. So for example, for this problem, we want to find the limit as n approaches infinity of a n plus 1 over a n. So the goal of this is to basically say we have the term after in the sequence divided by the term before, and if the limit as n approaches infinity of that exists, or depending on what sign it is, determines if the series converges or diverges. So if we take a of n plus 1, all it's saying is that we're plugging in n plus 1 for n. So all it's asking us to do is to take the limit as n approaches infinity of n plus 1 factorial divided by 3n plus 1, all divided by the original sequence of n factorial over 3 to the n. So if you divide this out, this is going to be, let me extend the page. If you divide this out, this is going to be the limit as n approaches infinity of n plus 1 over 3. And so, of course, you know that this series is going to diverge, or this limit is going to diverge, which means that this sum also diverges as well. Okay? Now for the root test is kind of a little bit easier to spot, and this is when we have something raised to the nth power, kind of usually a whole expression, like a fraction raised to the nth power. So let's take this sum, for example. We have the sum of 2n over 3n plus 1, and then everything's raised to the n. So we're going to, basically the idea is that you're going to get rid of whatever it's being raised to. So if we just ignore this, and then the idea then is to simply take the limit as n approaches infinity of what's inside. So in this case, this would be equal to the limit as n approaches infinity of 2n over 3n plus 1, which is equal to 2/3 because of a 2 and a 3, right? Because the n's are both raised to the first power. So we have 2/3. And since this falls within under 1, since this limit is under 1, we know that this series converges. Okay, next is the Next is the alternating series test, also known as the Leibniz test, as well. And the main recognition for this one is if you see alternating signs. So, for example, in like this problem, if you see a -1 raised to the nth power, or raised to the n plus 1, or anything else really, and then tagging along with an additional function, then that's how you know you're going to be using an alternating series test. So the conditions for using this test is that uh, is that whatever's tagging along has to be a decreasing function, and the limit as n approaches infinity has to equal 0. So for this particular example, this function attached to it is 1 over n, right? So as n gets bigger, the fraction gets smaller. So it is, in fact, a decreasing function. So we already have our first check right there. So now all we need to do is take the limit as n approaches infinity of 1 over n, which we commonly know is 0. So because that's equal to 0, that's our final check. So that means we know that the series converges. Anyways, I hope you liked this video, and just to summarize, make sure to first do the divergence test that we did at the very start for all of them, and next you want to simplify the expression and make sure to check for geometric, p-series, alternating, and then go on to the more difficult ones with the comparison, the limit comparison, the ratio root, and integral. Anyways, I will see you all later, and goodbye, everyone.